Okay, hi there. Let's prove a statement in topology. It's kind of a basic one, but we'll do it in lean, so it'll show to be uh, different than just on paper. So what we want to prove is given a topological space X on a type, so that's a type there, or you can think of it as a set, but really it's a type, and then topological space on that, and given some subset of X, A, then given the hypothesis that for all x and a, there is an open set U, that's here, such that x is contained within U and U is a subset of A, then A should be open. Um, you can sit and think about that. You can try it if you've never tried that before, but I'll explain how we're going to prove this. This is just one way, so you might come up with another. Um, the way we'll do it today is just, you know that if that's A, and you know for any point in there, there's some open set u. So if that's x, you get a ux. If you do that for every point in here, well, then you'd have a lot of u's going on, and you'd probably cover the whole thing eventually. And well, it actually does cover the whole thing because if you go over all the x's in A, the x's alone would cover it. But yeah, you're doing larger sets around those x's, so those definitely should cover it. And also, just remember, since each U is contained within A, they never escape. So our claim really is that we want to show that if you go over all the X's and A's and then you take like the U associated with that X, then that should be equal to A. And the reason why we want to do that in the first place is, well, we know these are open, right? So if those are open, then a arbitrary union of open sets is open, and then that would be showing that A is open. So we can get started with that. We'll go back to our statement here. Now the key thing about that is like we said, given a point x, we have like a way to immediately like associate that. So given some point x, we can associate it with that u associated with it, right? You can think about that as a function pretty much. So we kind of want a function that's going to take us like from a point there to like our set u. So it's just be like, I don't know, like f of x should be equal to like that associated thing. So, well, we can actually get that because since that's one of our assumptions, we should be able to get that function pretty easily. Uh, in MATLib, we have a tactic for that. It's called choose. Let's show that. Um, so we'll go to the tactics. Oops. So I'll just make it large. Why not? So uh, what is that called? Choose, right? So choose. So if you have a hypothesis where you have for all x for all y, it exists a, b, you can see that like the a and the b are allowed to depend on x, right? So, and also they're being used in here, but, and these two are functions. If you have that, like for any x and y, you get an a, which means like you can just have, that could be like a function mapping into the set a. So like given these two, we map into that point, and the same thing for b. So that statement is really just equivalent to having those two functions and then evaluating those functions at x and y. And then our hypothesis would look a little different. It'd look like that. You get two of each thing because we have one for A and one for B. Now, one that suits if we have um, propositional arguments like here, you want to use choose with the exclamation point. It'll make it simpler. So we'll try and do that. So we have to use choose. And then the first thing is what we want to call that function. We'll call it f. We'll call the new hypothesis that, and we'll use, I think it's using like h naught. And yeah, on the right hand side, you should be able to see the two things we got out of that. We got our function and we got hypothesis using that function here. So that's good. We want to show something's open now. But remember our goal. We want to have the a should be equal to the union over x's in a, and then we're going to use that f of x, which is the u associated with it. And to prove that, we'll have to open a block, and to show two sets are equal, you can show that their elements are equal. That kind of lemma is called an extensionality lemma, and I'll show you that. So here, it also works on functions, but the idea is the same. So given two functions with different definition, they give the same output on the same input. So even though internally they're different, externally they act the same way. First sets, it's the same kind of thing. If the elements inside of it are equal, then they should be the same set, even if they are produced a different way. So we can start by doing extp, which would change it to exactly what we've described. And to prove it by implication, we split to get leftward and rightward. And then to deal with each direction, we can open blocks and prove them. So in the first block, we have that P is in A, and we'd like to show that P is in the union uh, of one of over all of those U's. Given a union like this, we know that P is in the union as long as it's in at least one. So the way we can do that is with we can find something in MATLAB for this. You might not know it, but you'll learn from this video what it is. So it's mem union and then 2. So this will make sense once you see it. So given a union over some index set or whatever, and then you have some hypothesis that involves that previous variable you just used. I believe this is called 2 because there's like two things here. Because on this one it's just using 1, so there's some naming convention you can internalize. And then you have something involving uh, these two. So then that is the same thing as there existing sum where that's true. But yeah, just understand this one, and this should be an easy advancement on that. So okay, let's use it. But before we get there, we kind of have some work to do because it's not exactly to prove just that P is in the union, it's an implication. The way you can deal with an implication is you can do an introduction, hypothesis involving P, and then now we can use that mem union. So let's try that. So we can rewrite with mem union and then 2. And so we need to show that there's an I so that P is in Fi and that I needs to be part of A. Well, I see that P is in A and P is also an element of X. So if we evaluated it here, we could first get rid of the for all, then we could get rid of this, or not get rid of, but since that's true, we also would have this being true, and that would be X replaced with P, so P would be in F of P. So what can we do? I suppose we can just use P. So now our goal is to show that P is in A, which is that, and P is in F of P. Well, to get to that, we'll have to do some work, but we can use well, how about let's make like a temporary variable. So we could finish the proof on the next line, but instead we'll break it down a little bit. So let's make h of p be equal to, and you can see it breaks lean on the side, so I'll just comment it as I go. So let's let h of p be equal to hf evaluated at p, and then evaluated at hp, which will get us right hand side. So right now that's evaluating to everything here. And that's a whole bunch of ands together. In the bracketing, you can see that's one piece bracketed, and then you have that. And we want to get this part. So we're going to do a dot 2, which refers to the right-hand side, and then a dot 1. So, well, actually, let's just have this. We'll see what that looks like. So HFP is this. And now with HFP, we want to extract that, and we're going to use that. And when there's an and, you can construct the and using anonymous constructor notation, which would look like this. So we need to use HP, and then we need to use HFP, and then dot 2.1, and then we can close that off, and that constructs our and it finishes the proof of the rightward implication. So we'll move to the left now, and we'll intro HP, or sorry, maybe that was a little too fast. You can see that our statement to prove is this. Well, that won't, since these two are separate, I can also use intro HP since it's involving P. Maybe I should name stuff a little nicer, but that works. And now we have that. We'd like to prove P is an A. To prove that P is an A, well, the only thing up here I see involving something being an element of A would be this, because that says given some point in here, given some point M in fx, that implies that M is in A, which it looks like that. So let's see if we can do something with that. Well, we know it's in the union, which means it's in at least one fx for some x. So we can just start by rewriting like that. So we'll do a rewrite mem union. And by default, a rewrite would target the goal. So we need to do an at HP, so it'll actually target the correct thing. So now it's changed to there exists an I, which is an A, such that P is an Fi. And to get our I out of it, since it exists, since I and J exist, what you do is you do a cases HP with I, HI, so that's I, the element of X, and then HI is the statement that you get after you've extracted that out. You can do that again with the other. So we can do cases HI with, and then I will use HIA because it's actually a hypothesis, which you'll see in a moment, and then we can do HIA and then HP. I'll just call it Fi for now. You can see that makes sense since we have that capital I and the A there. So I've extracted I've extracted the element that existed where it held, and now we get this. Okay, well, to show P is an Fi, we would probably want an I here, which means we probably want to evaluate FH at I, and that's going to be good because we need to show that I is an A, and we have that I is an A. So we'll be able to get right hand side, which means we'll be able to get this. So we'll use a temporary variable again. I'll let it be t this time, and then we'll use hf at I, HIA, which will get us that right hand side since we're evaluating it there. Oh, and I think I've called it fh accidentally. So I'll just change. There's only two instances. So hf for, I put the h first because it's a hypothesis. So now we have the right hand side here, and we pretty much want to use this. By definition, that's an implication. So if we knew that P was an Fi, then P would be an A. Well, that's nice because that's what we would want to show. So I think at this point we can use an exact statement. I'll comment it out as I type it so it doesn't break it. And what we need is we need to do T. And if you remember how the ands work, we need to get that dot 2 is referring to this. This would be dot 1. And then dot 2 would be that again. So we need to do a 2 dot 2. And then, so now we need to evaluate this with the fact that P is an Fi, which would give us the fact that P is an A. So we would use HP Fi here, and that would prove it for us, hopefully. So yeah, as you can see, the goal is finished. There's more to prove though, because we've just done the main brunt of the work here, but there's a little more. So usually you would have to name this. I actually didn't, but it calls it this automatically, it looks like. So let's just go with a rewrite of this. And the reason why I want to do that is because our statement to prove is open A. Well, A is equal to this union, so let's get that union in there. So now it's in there, right? Isn't it? Just forgot a comma. So, oh, maybe not. Oh, I think I'm inside of a nested thing here, so let's get out of that. Okay, so rewrite this. Now we need to prove that the union of open sets is open. Well, um, I know of something in MathLib, which I'll teach you about, and that is open B union. So this just says that if we have a function that says for any I in S is open Fi, where F is a function mapping to those sets, then we know that their union is open. All that's saying is you have a collection of open sets, then their union is open. Um, since our goal looks like this, it would suffice for us to just show this. And the tactic to use in that case, when it suffices to show some hypothesis of a theorem to get the conclusion, is apply. So we're going to apply on this theorem. So we'll do an apply is open in a B union, which is what we just found. And our goal changes to showing that each set is open. And we know that shouldn't be too hard because we know that that's true because these are our u's associated with each x in our image from before. So to prove this, just looking at it independently, it's an implication with a for all in front. So we can introduce the I and then the assumption, which would be depending on I. Then we just need to show that Fi is open. Well, Fi would be open in here. So we kind of just want to evaluate HF at I and then at HI, and then we want to get that dot one out of it. So without commenting, since I think we can do it without keeping our eye on it for too long, we can do exact HF at I at HI, and then we need to make that evaluated at that first part of it, and that finishes our proof. Hopefully that's useful for you to see. Obviously this isn't going to be like the most, probably it's not the best way to do it since I'm uh, not fully experienced at Lean, but hopefully either you can learn something from it, or if you know how to improve it, I can learn something from it. But yeah, thanks for watching the video.